Okay, hello everyone. Welcome to the third lecture. So let me share my screen. Okay, so there was a holiday in between. So it has been exactly a week after the previous lecture. So let's do a quick recap of what we learned in lecture 2. So we discussed about regression problem, and we specifically considered this simple linear regression model, like which is W is equal to W0 plus W1x, right? And we also discussed about like what is a linear model. Like a model is linear in like a model is linear if it is linear. So like basically any model which is linear in terms of the parameters of the model is known as linear model. And then we derived the solution for least squares. So this was a summary. So the model can be represented as W transpose X, where W is the parameter of the model, and the objective function was a least square objective function, where like this is like the matrix notation, but like in simple terms, it's just y minus wx the whole square, right? So, and we also derived the solution for this problem by differentiating this objective function and setting it to 0. We discussed that least squares might not be the like a good metric like to consider, because it is a square and also it is dependent on n, which is the total number of examples. So instead we derived this RMSE, which is starting from the least square error, but like correcting the mistakes that least square error had, right? So then we went to a synthetic example, and we found that the simple linear regression model is not good enough to capture nonlinear trend, and we resorted to polynomial regression, like where instead of just doing W0 plus W1x, we had W0 plus W1x plus W2x square and so on, right? Like so if you have m, you can model an n degree polynomial with m plus 1 parameters, where the m plus 1 parameters for the bias. Okay, and then we discussed how to make it as a vector notation. It happens that it's the same W transpose X, and it's still a linear model, and the same solution applies here too, right? Like, and we looked at the solution for various degrees. So you can see that degree is equal to 2 still looks like a line. Degree is equal to 3 or 4 looks close to the true function. And from degree is equal to 5, like if you look at 6 or 7 or 8 or 9, the function that the polynomial regression is learning is deviating from the true sine function, right? And if you look at, especially if you look at degree is equal to 9, you have 0 training error because this function exactly fits all the lines. But if you look at the function, like since we already know that the true function is sine function, we can see that this is not a good approximation of the sine function, right? Like so, or in other words, this function has poor generalization. When you use this function to make predictions for an unseen example, it's going to perform very badly, which is known as overfitting. And we found that as you keep increasing the number of polynomials, at some point, like in this case, it happens at degree is equal to 9, you have a 0 training error, but very high test error, right? So there is this good region, which is like degree 3, 4, 5, 6, but after that, your model starts overfitting, right? Like so now we also discussed why should this be the case, right? Like, so for example, we know that the 9-degree polynomial can represent a 3-degree polynomial by just setting the rest of the degrees to 0, like by coefficients of the rest of the degrees to 0, right? Now, that is not what is happening in reality. So what happens in reality is, like, as you keep increasing the number of degrees, in m is equal to 9 case, you have 10 parameters and there are only 10 examples. So these parameters are heavily tuned for these examples. So we stopped here with the question of like how to solve this problem of overfitting. Okay, so that is a quick summary. So now let's start from where we left. So how to solve this issue of overfitting? Okay, so any answers to begin with? You can raise your hand and you will be unmuted. Okay, there is also there's a chat.
All right, so well, I was thinking maybe one answer would be to increase the number of data points, so we wouldn't be fitting as thoroughly through every data point if we have more, but it's not always possible. So I'm guessing it's not the correct answer.
Well, that is fine. So like the solution is like you add more data points so that like you have add more data points so that like you have like you don't have this issue of having same number of parameters as the examples. That could help you. And there are also other suggestions in the chat. So people suggest to reduce the number of features so that you don't have a lot of features to overfit to the small data set that you have. And there are actually many more good answers. I'm not going to tell them now because that's what this lecture is all about. Okay, let's start with the first simple solution. So solution one is to basically add more examples. Okay, so that the model cannot overfit. Okay, now here is the same sine curve problem of like data. In this case, like here you can see that in the left figure, I have used 15 examples instead of 10 examples. Okay, now you can see that with degree is equal to 9, you cannot perfectly fit these 15 examples. So the model is like not too far from the sine wave, like it is still far from the sine wave. But as I add more example, in the right side, you see that I have 100 examples. When I have 100 example models, like the 9-degree polynomial is actually going to, like, it's almost close to a 3-degree solution, right? So now this looks like a sine curve. So this approximates the true function very well. But as someone rightly pointed out, it is not always possible to add more examples. So what can we do in such situations, right? Like, so let's say data is rare, I cannot add more examples, and my model is overfitting. Now what can we do? So now this is where the second solution is going to be useful. So the second solution is based on the observation that when you have more parameters and like less examples, your parameters are blowing up so that it is heavily tuned for these examples, right? So now if we can somehow reduce this blowing up of parameter weights, then we could control overfitting. So the second solution is to add a penalty term to the error function, okay, in order to discourage the coefficients from reaching large values. Okay, so here is one example of how to do that. So I'm going to take my original error function, which is basically 1 over 2 summation n is equal to 1 to n y hat of x n given w minus y of n. Okay, so this was my original error function. Now I'm going to modify this error function. Let's call it e dash or e hat. Now I'm going to add an extra term, which is the norm of the weights. Okay, and I'm going to put a lambda by 2. I'll explain why. Okay, so now in this case, the like W square is essentially W transpose W, which is basically W0 square plus W1 square plus Wm square. Okay, now this specific, okay, so this specific term that we are adding here is known as a regularization term. Okay, essentially, when I minimize this function, I'm not just minimizing the least squares, I'm also minimizing, I'm minimizing the least square in a way that my W is going to be minimum as well. So this objective function makes sure that W doesn't blow up, or in some sense, it is regularizing the the training procedure here. Okay, so now what is this lambda? So this lambda is called as like regularization coefficient. Okay, so now this coefficient controls the relative importance of this regularization term. So if you have a very high lambda, then basically means that you're giving more importance to reducing the magnitude of W. If you have very low lambda, it means that you're giving less importance to like reducing the magnitude of W. Okay, so now let's look at this error function. This error function is still a quadratic error function, like a quadratic function with respect to W, right? So this solution, this function still has a closed form solution. Probably we are not going to derive the closed form solution for this regularized linear regression, like regularized regression model in this lecture. But just know that this particular error function is quadratic, and hence we can actually come up with a closed form solution for this. For the moment, let's assume that someone has given us this solution. Okay, so someone has given us a solver which will help us to find the W which satisfies this error function. Okay, so now how would such solutions look like, right? Like, so now in this case, like, okay, one thing in this graph is like we are going to work with ln lambda instead of lambda, because the range, it has a higher range. So in this case, you can see that the true function is given, and also I have a degree is equal to 9 polynomial regression with ln lambda is equal to -10 or lambda is equal to 3. So from this, you can actually derive the lambda, but lambda is simply e power ln lambda. Okay. The only reason why I'm shifting to ln lambda is like it gives us a big range for the coefficient. So now you can see that when I have lambda, like when I have like some strong coefficient, in that case, okay, so as I increase the value of lambda, you can see that the solution goes close to a linear solution, right? So on the other hand, like with the right value of lambda, we can actually get a reasonable function which looks like the sine curve. So let's also look at the weights learned by these two different values of lambda. Here you can see that ln lambda is equal to -infinity means lambda is 0. So this is no regularization. Okay, and this ln lambda is equal to 3 is too much regularization. Okay, so now, okay, there is a question if lambda is always positive. It doesn't make sense for lambda to be negative. So the lowest lambda can get is 0. So if I put lambda is equal to 0, then the second term disappears. So there's only the first term, which is the regular linear regression. Okay, so now we can see that when lambda is small, when lambda is too small, okay, or 0, okay, in that case, then there is no regularization. Okay, but when lambda is high or too high, then you have too much regularization. So there is, okay, so now someone has asked the question, which is what I was also about to ask. So why do, like, how, it looks like it is very crucial to choose the right lambda, right? Now, how to choose the right lambda? How to choose the right lambda, right? So this lambda, which is something that we pick by ourselves, right? Like is known as a hyperparameter
There's a question, Sharath.
of the model. Yeah.
Yes, I have a question.
Yeah.
If I say I just want to set lambda to 0, is there a rule where I can choose the polynomial degree without, just based on the quantity of data that I have?
Well, like, when you do lambda is equal to 0, then you are just doing simple polynomial regression. And in that case, you could try different values of the polynomial. I will come to that solution like very soon.
Okay.
Okay. Okay. So this lambda.
There's one more question by Alexander.
Yeah.
Okay.
Yeah, I would just have a small question.
Yeah.
You said that lambda was a you were saying lambda is a hyperparameter. I would
Yeah.
just like to know what's the difference between a parameter and a hyperparameter.
Okay, that is what that's what we are going to see now.
Okay.
Okay, so this is a hyperparameter of the model. So now, what is the difference between hyperparameter and parameter, right? So normally, parameters. Okay, we have parameters. In this case, W is the parameter, and we have hyperparameter. Okay, so normally we will be fixing the hyperparameter before training a model. You fix your hyperparameter, okay, and you will be learning your parameters from the data. From training data. Okay, now the question is, how do I fix this hyperparameter, right? So I can try a bunch of hyperparameter values, right? Like I could try lambda is equal to 5, like ln lambda is equal to, I don't know, ln lambda is equal to -5 + 5 and so on, right? So I could try a bunch of values. Now the question is, how do I choose which is the best lambda, right? So can I use the test set to choose lambda? So we are going to do a template poll here. Don't answer in the chat. So can I use a test set to choose the value of lambda? So A, yes, B, no. Okay, so I will be ending the poll soon. Okay, so, well, it looks like 30% of you think you can choose using the test set, and 70% of you think that you should not use the test set. So remember from the previous lectures that your test set is a proxy for the real performance. So if you are going to use your test set to choose the lambda, then in some sense your model is seeing the test set, right? So then the test set doesn't become a proxy for the real life performance. So you should not use the test set to choose your lambda. So if you're choosing your lambda by using the test set, like whatever model which gets best performance in the test set, then you are essentially cheating. Okay, so now the next obvious question is, can I use the training set to choose lambda? So we will do another poll. So press A if we can use training set, B, no. I'll be stopping the poll soon. Okay, so it looks like a 50-50. Some of you think that you can use the training set to choose lambda. Some of you think no. Well, the answer is again no, because remember that if you're going to choose your lambda based on the training set, can someone tell me what would be the best lambda? Yeah, so the answer is 0. You don't even need to look at the test. You don't even need to look at the data, because the regularization term that we add here, where's the equation? Yeah, the regularization term that we add here is essentially an extra constraint, right? Like, so this is going to interfere with the first objective function that we have. So if we are going to, if your goal is to minimize the training error, then ideally, like, you can just set lambda is equal to 0 so that you can focus just on minimizing the training error. So choosing your lambda using the training set is not a good idea, because in this case, lambda is always going to be 0. Okay. Now, how do I choose lambda, right? Like, so I need to find this lambda, but I cannot use either the training set or the test set. Okay. So now this is where we are going to divide our data set further into another new set. Okay. So now we are going to, instead of dividing the data into train and test, we are going to divide our data into train, valid, and test. Okay. So now this validation set, right, is a special set that we are going to use just for hyperparameter tuning. Okay, so now given a data, like the data set, now I will use the training set to train a model. I can try multiple types, multiple lambda values. And for every lambda value, I will look at the validation performance. Okay, now you have the validation performance for, like, let's say 5 models, and like you pick the best one, and that is your final model. So now you can do your test, which is a proxy for real life performance, with the final chosen model. Okay, so let me summarize the process here. So the way in which we will typically find the lambda is like this. First, for different values of lambda, we will be training the model, and then we will be computing the performance in validation set. Okay, so then we will pick the value of lambda that has best validation performance. Okay, so now once you pick the best lambda, let me finish this. So then you compute the test performance for the model with chosen lambda. Okay, so now this simple process of finding the lambda using validation set, right? So this is known as model selection. So often when you work with a model which has a hyperparameter, you need to find the best hyperparameter for that model by using your validation set and model selection. So here you can see that for different values of lambda, this is the training and validation performance. So note that I am not plotting the test performance here. You should not see the test performance for different values of lambda. So if you see that, then you're cheating, right? Like, so there's no use in using the test set as a proxy. So we are just using the validation set here, and you can see that this is like this seems to be a good region for lambda. So I would normally pick the lambda which has the lowest validation error, like in this case, I probably this point, right? Now that is the lambda that I will pick. I will train the model for that lambda and do the test performance. Okay, so what was the question?
Yeah, okay, go ahead.
Hello, can you hear me?
Yeah.
Yes, thank you. I just want to make sure that I get it right. You said that we cannot use the train sets to look for the lambda.
Hmm?
What if we don't have enough data? I mean, we cannot split the data into three parts.
Well, okay, that's a good question. No, okay, so when you don't have enough data to spread it into three parts, like we will talk about like other things like like k-fold cross validation and like some other methods. So, but probably a bit later in the course. But in general, like given like whatever data you have, it's a good idea to divide it into three sets. If you cannot divide it into three sets, like we will discuss about those extreme situations in the future.
Okay, but if we can't split it in three sets, can we at least try to find the hyperparameter with the trained data set?
No, there is no use in finding a hyperparameter with the training data set, like because if you just use your training set, your hyperparameter, like lambda is always going to be 0.
Okay, thank you.
There are also other ways of there are many other ways to tackle this problem, but probably this is too early to discuss them.
Okay, thank you.
Okay, okay,
Yeah.
so
Go ahead. There's one more down.
Sorry, can I ask you a question? How we can ensure that the valid test follows the same distribution of the test or training set?
okay, so that is a good question too. So I told you to split your data into train valid tests, but I did not tell you how to do this splitting, right? So normally when you split your data into multiple sets, you should make sure that you are maintaining the same distribution in all the three. Probably we can talk about that like once we move to classification. So yeah, so that's also a question that we will answer very soon. Okay, so now I'm trying to answer the previous questions. So now someone raised this issue that, okay, so can I pick the degree of the polynomial instead of like having a lambda, right? So that is another way to solve this problem. So in this case, we know that the solution for this problem is a 3-degree polynomial, right? But in real life, like we might not know the solution, like what is the ideal polynomial that we want, okay? So what if the ideal polynomial degree is 20, but I start with a 15-degree polynomial model and do regularization, right? Like now it is of no use. So if I start with a 15-degree polynomial, I can do regularization to only recover polynomials of degree less than 15, right? Like if the true degree is 20, then it is of no use, right? Like so now how can I solve this issue, right? Like so now that brings us to the third solution, which is basically based on the fact that m, the degree of the polynomial, is also a hyperparameter. So now that we have a separate validation set, what you can do is try different values of m, like degree 5, degree 10, degree 15, right? And look at the validation performance. Now you can pick the degree which has the best validation performance. In this case, we are not doing regularization, but we are directly tuning the degree of the polynomial. So this is also model selection. In this case, you're doing model selection by considering different degrees of the polynomial. In the second solution, you are doing model selection by varying the importance in reducing the magnitude of your weights. Okay, so now, okay, so we have discussed some solutions for overfitting. So overfitting, in some sense, is one of the central problems in machine learning. So you cannot, like we will discuss about overfitting again and again in this course. So one reason why it is persistent is the fact that often it is easy for us to start with a higher expressive power model and regularize it than starting with a model which does not have enough capacity. So this example actually highlights that. So if my data set comes from a 20-degree polynomial, starting with 15-degree polynomial is not a right thing to do. So probably it's better if I start with a 100-degree polynomial, in which case there will be overfitting, but still I could regularize and control this overfitting to discover or like find the 20-degree solution. So that's about overfitting. Now that we have seen one example machine learning problem, which is like which is regression, I would like to show the basic machine learning pipeline. Okay, so given any prediction problem that you want to solve, this is the sequence of things that we will be doing. So the first step is to define the input and output. Okay, so what is X and what is Y? Okay, then the second step is to collect examples for the task. Okay, then the third step is to divide this example into train, valid, and test set. Okay, then you would do some data pre-processing. Which we will discuss a bit like as we progress. And once you have a pre-processed data, then you will be defining your model. Okay, so now this model will have both parameters and hyperparameters. Okay, now once you define your model, you should also define your error function that you want the model to minimize. Okay, so now define the error function, or you could also call that as loss function you want to minimize. Okay, now once you have the model and the error function, okay, I have wrong numbering in the notes. Okay, so for different values of hyperparameters, you will learn the model by minimizing the error function. Okay, then you will compute the validation performance. Okay, now you will use this information to pick the best model based on validation performance. Okay, finally you will test the model with test set. Okay, if you are happy with the model, you will be deploying it in your solutions. If you are not happy with the model, then you will ideally go back to defining a new model and then going through the whole process again. Okay, so now this is the complete pipeline of a machine learning application. Now, it is too much to cover all the aspects of this machine learning pipeline in the first introductory course. So for this course, we will be focusing on certain aspects of this pipeline. Like for example, we will not talk about how to collect examples. We will not talk about how to define your input and output. We would often work with some standard data sets which are already predefined, and like certain things that we would focus on are like how to divide your data into train, valid, test set, and how to define your model, like the parameters and hyperparameters, and how to choose a specific error function or loss function for the model. And we will spend a lot of time on how to minimize this error function, which is basically an optimization problem. And we will also spend some time on how to pick the best model, which is basically model selection. So now these are the key aspects in the pipeline which we will focus more on. However, we'll be touching other aspects as well, like once in a while. Okay, so now let's move to a new type of prediction problem. So we have seen a regression example. Let's also see one classification example.
Sharad, we have a couple of questions.
Yeah.
Doesn't data processing come before splitting?
Well, there are certain data processings you cannot do before splitting. So we will talk about that later.
Yeah, and instead of trying different hyperparameters.
So, okay, so for example, like, okay, just to complete the answer, for example, if you are doing certain data processing which looks at the data, right? Like, so, like, if you then you are indirectly seeing the test set through the data pre-processing. So it's better to divide your test set separately and then do your data pre-processing.
And there's one more question. Instead of trying different hyperparameters, why not just use cross-validation to find it?
Well, in some sense, like what we are doing in the model selection is similar to that, right? Like, so we will see how to do cross-validation in the future, but like you could do model selection as we discussed today, or you could do cross-validation. Okay, so let's move to the let's look at one classification example. Okay, so now in this case, like, we are going to work with some synthetic data that I have created. In this case, there are two features, x1 and x2, and x1 and x2, and we have two classes. Okay, so we have a blue class and orange class, and we have 100 examples for each class. Okay, now the goal is to, given a new circle, I want to classify it as either blue or orange. Okay, so let's try this game. So let's say I have a new circle, the red circle that I have drawn here. Okay, so now I want you guys to do this template poll, A for blue and B for orange. So A for blue, B for orange. So what class do you think this particular red example is? Okay, can we have your votes quicker so that we don't spend 1 minute for every vote? As a policy, let's just do the vote for 30 seconds. So you have to answer within 30 seconds. Okay, I'm stopping the poll. The majority is blue, but I'm surprised that there are actually 20% of students who think this is an orange. So maybe I chose well, like, first of all, we don't know whether it is blue or orange, but like most probably it's a blue thing, right? Like, because it's surrounded by blue. Now, similarly, like if I give another example, like which is in the top left, right? So it is most probably orange, right? So how do we make up our mind like this? Like, it's because in some sense we think that similar, like examples which lie closer to each other are going to come from similar class. Okay, so now can we come up with a mathematical model which will decide, given a new data point, whether it is a blue class or orange class? Okay, so that is a task. Let me erase these things. Now, often when you start with the classification problem, the first thing that you will do is to give numeric values for these classes, okay, to make sure that like we can actually write the model in a mathematical way. So let's say we are going to say blue could be class 0 and orange could be class 1. Or some people also use -1 for one class and +1 for another class. So you could use any numbering scheme that you want. So let's go with 0 and 1. Okay. So the moment I convert these categories into numbers, is there any way in which we can use whatever we have learned before to solve this problem? Anyone who wants to answer by raising your hands? Okay, there's someone raising hand, I guess. No. Nicola, I guess.
Yeah. Right. Yeah, Gus, and you can unmute it.
Yeah, we could do some algorithms like K-mean or something.
No, my question is how can we use whatever we have learned so far to solve this problem?
Yeah, all right.
Nicola, Sharon, can you unmute Nicola?
Yeah, I have unmuted.
If we pick a new point, maybe we can choose like a radius around that point and
Okay, so I'm not asking for a new solution. My question is how can we use whatever algorithm we have already learned to solve this problem?
Right.
Okay, so maybe I will continue with the answer. So like the moment I convert it into like something like 0 and 1, then I have x1, x2, like some value, right? And the corresponding y is given by either 0 or 1, right? So now this could be considered as a regression problem, right? Like you're just regressing, instead of having the entire real line as possibilities, you only have zeros and 1. That is okay, but you can still use the linear regression solution that we already have, right? Like the simplest way to use linear regression here is in the case of 0-1 classification. Okay, so you have y hat. You can come up with a classifier which says y hat is 1 if my regression value is greater than 0.5, 0 if my regression value is less than or equal to 0.5. Similarly, for -1 classification, I could say y hat is equal to -1 if y hat the value is less than 0. It's +1 if the value is greater than or equal to 0. Okay, in some sense, y hat is equal to 0.5 is known as the decision boundary. So anything which lies above 0.5 can be classified as class 1. Anything which lies below can be classified as class 0. Similarly, for the second example, y hat is equal to 0 is the decision boundary. Okay, so now let's look at how such solution would look like. So now in this case, you can see the result of using linear regression that we have already learned before for this classification problem. Okay, so now this is a linear model, okay, without the bias term. So this is essentially y is equal to w0, so w1x1 plus w2x2. So this is my linear regression model, and you can see that the blue region corresponds to blue class and orange region corresponds to orange class. Okay, and this line is my decision boundary, which is basically w transpose x is equal to 0.5. Okay, so now, you can see that this model has a lot of error, right? Like by just looking at this graph, you can say that there's a lot of orange circles which are wrongly classified as blue, and there's a lot of like few blue circles which are wrongly classified as orange, right? The error by this model is so high. Now maybe, okay, this model is restricted because there's no bias term, right? Like you can see that it has to go through 0. So what happens if we remove this restriction? So now this is again linear regression, but with bias term. So in this case, y hat is given by w0 plus w1x plus x1 plus w2x2. Okay, now as you can see, this model still makes some mistakes. There are some blue points classified as orange, some orange points classified as blue. Okay, so now how can okay, now can we come up with a better classifier other than this reused linear regression model, right? So someone started telling me this solution, which is which is a new algorithm that we will introduce now. So, which is the idea of using nearest neighbors. Okay, so now this is a very simple classification algorithm where the idea is look at your neighbors. If you have a lot of orange neighbors, then probably you are orange too. Similarly, if you have a lot of blue neighbors, then probably you are blue too, right? So that is why when I draw a line here, like everyone guess that it is going to be yellow. Like you say it is yellow because there is a lot of other yellow, like, sorry, you say orange because there's a lot of other orange circles there, right? Like similarly, when I draw a new data point here in the bottom right, you would classify that as blue because a lot of its neighbors are blue, right? Now, how can I express this mathematically? So mathematically, y hat of x is going to be, I'm going to consider a bunch of neighbors, okay, and take an average of their classes. So the nk of x here is basically the neighborhood of x. So in some sense, you could call k closest points xi in the training data. Okay, so how do I define what is close? Like one simple solution is to use Euclidean distance, like what are the data points which are close to me in the Euclidean distance? Okay, now once I compute this average, if this y hat is greater than 0.5, I will choose class 1. If it is less than or equal to 0, like 0.5, I will choose class 0. Okay, so in some sense, what we are doing here is like we are doing majority voting. So if I have 10, let's say I pick k is equal to 10 neighbors. With 10 neighbors, if there are 7 positive, like 7 class 1 neighbors and 3 class 0 neighbors, then the score here is 7 by 10, which is 0.7, right? So probably this class is class 1. Okay, so now this nearest neighbor solution, right? So this basically assumes that the class distribution is locally smooth. We assume that locally, like all the examples in one particular local region is going to have similar classes. Okay, so now what is the hyperparameter for this algorithm? Maybe let's just ask people to type. So what are the hyperparameters for this algorithm? Okay, so number of classes cannot be hyperparameter. It is given in the task. So one answer is 0.5 itself, right? Like, and some people say k, right? So k is the most important hyperparameter here. So depending on the number of neighbors you choose, your decision might change. Okay, there is a lot of k, and there is also Euclidean now. That's good. Okay, so now let's see what happens when I choose k is equal to 10. Okay, this is an example where I choose k is equal to 10. Okay, so when I choose k is equal to 10, you can see that we can actually start seeing like really complex decision surfaces, which was previously not possible with linear models, right? So you can see there's an orange region, and within the orange region, there's a small blue region, and so on, right? So now in some sense, it has a very irregular decision boundary. It seems to be looking good in terms of accuracy when compared to linear model, but there are still some misclassifications, right? So now let's consider what happens when I use k is equal to 1. Okay, so now this is an example where k is equal to 1. I just pick one nearest neighbor, and you can see that there is no misclassification here. So does that mean k is equal to 1 is a good KNN model?
So there's one doubt, Sharath.
Yeah.
Mohammed, go ahead.
I don't know.
Okay, you have to unmute Mohammed.
Yeah, yeah.
It's okay. It's okay.
It's okay.
Okay.
Okay. Okay. So now again, like, so we know that we need to choose the right hyperparameter, right? Because for certain values of hyperparameters, you might overfit. So that is exactly what happening in k nearest neighbor too. So in this case, the x-axis is the value of k and y-axis is the error. Okay. Now you can see that when k is equal to 1, your training error is 0, but your test error is so high. Okay. And as you keep increasing the k value, like, so like you can see that there is a sweet spot here. Like, what is the sweet spot? So the sweet spot is somewhere here, right? So this is the place where your validation error is really low. And I have also plotted the accuracy of the linear, the error rate of the linear classifier. So the linear regression model. And you can see that the linear model has almost 0.26 error rate. The error rate should be close to 0. And the k nearest neighbor is doing better than linear model, like which is kind of understandable because k nearest neighbor can have complex non-linear decision boundaries, which is not possible with a linear model, which can only draw a line, right? And as someone rightly pointed out, the hyperparameters for this model, it's not just k, even the metric that you're using to compute the nearest neighbors. You could use Euclidean norm, but you could also use other sort of distance measures depending on the task. Okay, so I will stop here. And we will, I think this kind of concludes the introduction. We will get into more detailed stuff from next lecture. So next lecture is as usual on Mondays. I will stop the recording here and then I will take some questions.
There is one question.